Hey, guess what time it is, class? It's science time. Now take out your notes and let's get learning.
How you doing? Hopefully all of you are doing well. So today we're going to be going over equilibrium reactions. And one thing I would recommend doing before you get started, if you have not already, watch the video that I did with my son when we were demonstrating moving water from one container to the other one here and what was going on during that time. And one thing hopefully that you had observed was that initially you had a large amount of reactants, and then as time went on, more and more products are being produced here. But at the same time, too, my son was dumping this stuff from the product back into the reactant container. And we ended up reaching a point of equilibrium. And even when we tried changing the size of the scooping cups that we were using here, if I had a large amount and he had a small amount, eventually it would reach a point of equilibrium. And if we switched it, the amounts in each container would switch, but eventually it would reach a point of equilibrium. And sometimes it took a little bit longer than others, depending upon the size of the cups and everything here, but it would always reach a point of equilibrium. So before we get started here, we need to define a couple of terms here and just refamiliarize yourselves with some of these terms here. A reversible reaction is a chemical reaction in which the products can react together to reform the reactants. In other words, a lot of times we look at reactants turning into products, but now we're also going to be looking at products turning into reactants, such as, like in this case here, we have the reactant A producing the products B and C. So this is a decomposition reaction, but with the double-sided arrow. And if you remember, sometimes the way this is written out, where a lot of times we'll kind of look at it this way, where the reactant turns into the product. But in this case here too, is you can also have where the products turns back into the reactants. So such as in this case here, you have A produces B and C. So one substance that will do that is mercury oxide. When you heat it up, it will decompose into mercury and oxygen. But then also, this reaction is reversible. So you could take mercury and oxygen and combine them together to make mercury 2 oxide. So the forward and reverse reactions can occur at the same time. And at some point, the forward reaction rate will equal the reverse reaction rate. So how quickly the reactants are turning into products will be the same amount of time as the products will be occurring at the same rate as the products are turning into the reactants. So when this occurs, the reaction has reached what's referred to as equilibrium. In other words, there's no change in which is taking place between the reactants and products. Now, there's what's referred to as a dynamic equilibrium. So it's a state of balance between two opposing activities. The forward and reverse reactions are still taking place, but no overall net change in the equilibrium state. And again, if you remember with the video between the dumping the water in between the two containers, is that every time I was taking some of the water, dumping into the product, at the same time, my son was taking the stuff from the product and dumping into the reactant container. And it would always reach a state of equilibrium. So even though there's a movement of material, it's dynamic. The net change always remains the same. So the concentration of reactants and products remains constant. And the concentration of reactants and products can be different from each other, but still remain constant. So in other words, again, that was trying to show that here, where even if you have two different sized cups, so if you have a large cup and a smaller cup, eventually it will reach a point of equilibrium. It won't be the two containers holding the water in this situation were not the same amount, but eventually it would reach a point where there is no net change that's occurring in either one of those. So the equilibrium can be attained from either the forward or the reverse reaction. This can only occur in a closed system, so neither reactants or products can leave the system. So that's what I'm trying to show here with these two jugglers here. If you've ever seen some of those juggling acts here where you have two jugglers passing the pins back and forth. They always have the same number here, but as soon as one would leave, the other one would catch it here. But it really, at any one point in time, they're always holding on to the same number of pins. But even though they're transferring it from one juggler to the other one here, so they're always moving back and forth. So it's dynamic, but there is the amount on each one is always remain the same amount. So you could also have a static equilibrium where if you just stop juggling and just hold on to the pins, that would be a static equilibrium. But in chemistry, when these reactions are taking place, there's always a transfer which is taking place between the two. So it's a very dynamic equilibrium. Now, when I mentioned about it occurs within a closed system, an example of an open system would be if you were to have, say, like a container of water. So let the little red circles here represent water, and then you have like some sort of cup or some sort. So an open system will never reach a point of equilibrium, or it will be trying to achieve it, but it will never be able to successfully achieve it. And so what you're basically are seeing here is like the evaporation of water. And the longer that this takes place here, the particles, in this case being water here, will constantly be lost to the atmosphere. And so if I let this go on for a long enough period of time, eventually all the water that's within this container will disappear. So it would just been a single direction here where you would have liquid water turning into gaseous water. Now, closed system would be something like this. So for example, if I have, let's say again, it's water, and I put a jar over this, initially, in a closed system, it will be in a state of equilibrium. So in other words, the particles will be leaving, and eventually it'll reach a point where it should achieve a point of equilibrium. And this is very temperature specific. So in other words, at this point right here, this is now, we're kind of imagine here that this has reached a point of equilibrium. So there is a certain number of water particles that I can have as a gaseous phase, and a certain amount that's going to be in a liquid phase. If I were to heat this up, what would happen then is I would perhaps lose even more of these things. So if I heat this up slightly more, I would have maybe like another layer of these circles rising up here. But eventually it will reach a point of equilibrium. If I cool it down, I may have only lost a few of them. So a lot of times the equilibrium is very temperature specific. Now, once it reaches a point of equilibrium, then it will be very dynamic. So in other words, it just does not stop where this is only a liquid and this is only a gas. Instead, what happens is that the particles will switch places. And so, even though this is the total number of particles here in the gas, the total number of particles here in the gas is a fixed amount, and there's a fixed amount of the liquid here. They're still changing places, but the thing is that it's a very dynamic system. So it's kind of like the jugglers here, where they're tossing the pins back and forth, but there is going to be a fixed amount of particles here as a liquid and a certain number of particles that will always remain as a gas. So initially, again, when we first put the cover on here, it was not at equilibrium, and it'll keep losing in this case, the water molecules to the atmosphere. And once the atmosphere becomes saturated, it will reach a point of equilibrium. And when it reaches a point of equilibrium, then these particles will begin to switch places. So a gas will turn back into a liquid, and a liquid will turn back into a gas. And so this is a constant rotation which is always taking place. Isn't that amazing graphics? I know, Mr. Souder, that's really cool. Now, there's several different types of equilibrium. There's also what's referred to as phase equilibrium. So phase equilibrium, since the phase changes are reversible in a closed system, a state of equilibrium between the phases can be achieved here. So This is just like with the water. When solids or liquids are confined in a container, equilibrium will be reached when there are enough particles of a gas, such as typically like a vapor, to cause the rate of return to the original phase to be equal to the rate of escape. This causes a characteristic vapor pressure of a substance at a given temperature. So let me go back to this here again. Is that, depending upon the amount of space and the temperature here, once the air here becomes saturated, it's actually beginning to put some pressure down on the surface of the water. And that pressure will kind of prevent a lot of these from constantly be going off here. But that's not to say here that once it reaches a point of equilibrium that they can also switch places. In other words, a liquid turning into gas and a gas turning back into a liquid. So basically that's what's referred to as a phase equilibrium, is that in a closed system you will have some of the particles turning into a gaseous state and the gaseous state turning into a liquid or sometimes even a solid state. It can also even happen between like solids and liquids. The same thing can happen with that as well. Even like a floating ice cube in water can be at a point of equilibrium if you were to maintain that temperature. So some of the liquid water will turn into the ice, and some of the ice will turn into a liquid water. Now you can also have what's called solution equilibrium, so gases and liquids. So and the equilibrium is reached between the gas dissolved in the liquid and the undissolved gas above the liquid. Equilibrium is affected by temperature and pressure. The low temperature and high pressure favor solutions of gases. Carbonated beverages stay carbonated best when tightly closed and chilled. So this is just like in pop here. I mentioned this here before. Is that if you were to take a bottle of, let's say like a 2-liter pop bottle, and you shake it up, there is a point of equilibrium here. In other words, there's a little bit of a gas up there on the top, and some of that gas is dissolved into the liquid. But then also, if you agitate it, some of this gas within the liquid will turn back into a gaseous state, and you'll feel the pressure begin to go up. But if you let it sit for a period of time, it will go back to its state of equilibrium again, and eventually will end up returning back to the point where there is some of the gases will turn back into the liquid state here. But you'll always have a little bit of the gas, and also some of the gases being dissolved into the liquid. So this is one thing that, if you ever notice this here too, is that if you pour a pot of water and you put it on the stove, you begin to heat it up. And after the water begins to heat up a little bit, you'll start seeing these little tiny bubbles start forming on the surface. And that is not boiling. That's actually the dissolved gases in the water that are beginning to escape. Typically, cold water is able to dissolve more gases than warm water, which sounds kind of backwards here because we're so used to thinking that with warm water you're able to dissolve like stuff like salt and sugar. But warm water is good at dissolving your solids, such as like salt and sugar, but it's less able to dissolve gases. But if the water is cold, or the liquid is cold, it's actually better able to dissolve gases, but less able to dissolve solids, which sounds kind of odd. But that's what's happening with the carbonated drinks here, is that they're able to dissolve more gases when they're cold. If you heat it up, if you ever had warm pop, it loses its fizz really quickly. And then solids and liquids equilibrium. Solid added to a saturated solution will fall to the bottom instead of dissolving. So in other words, if you were to take some water and you start putting salt or sugar into it, and you keep stirring it up, eventually that solid will begin to dissolve. But once the liquid becomes saturated, if you add any more to it, the solid will just settle down to the bottom. You will not be able to dissolve anymore, and that's at the point of saturation. But the thing is, at that point of saturation, it's also now reached a point of equilibrium. So the equilibrium is reached between the dissolved solute and the undissolved solute when the rate of dissolving equals the rate of crystallization. So let me show it to you this way here. Now technically this is not a closed system, but just kind of give you It's somewhat of a closed system, but actually it's not really a closed system here. So let's say you're growing salt crystals, and so you have a solution of salt water. So you have aqueous sodium chloride. You have a little bit of salt growing on a piece of string here. That's what I'm trying to symbolize here. This is a length of string. And you have a salt crystal that's forming on here. Now, what's happening is that when it reaches a point of equilibrium, or basically when this solution becomes saturated, what's happening is some of the sodium chloride that's in a solid state will actually dissolve. But at the same time, once it dissolves, some of that sodium chloride will recrystallize back into a solid. So it will reach a point of equilibrium here. So if I were to cap this off, if I already have some salt crystals already beginning to grow inside of here, if I cap this off, you'll actually, over a very long period of time, you'll see some of these crystals begin to, say if I had this large crystal here, sometimes they'll start shrinking, but then you will have another one, they'll start growing. The total mass of the solid will always remain constant. And I've had many times here before where, sometimes in the past, where we've grown crystals, is that you may have one crystal over here, but if you had this little tiny crystal over here, sometimes this large crystal will start dissolving, and this one will start growing. And then sometimes I've had it where all of a sudden this one starts growing, and then all of a sudden another one starts growing, and then this one will start shrinking, and this one will start growing over here. And so, but the neat thing is that the total sum of the solid mass will remain constant. Now, typically whenever you're growing crystals, you would have this as an open system. So it will still go through this process of the solid turning into an aqueous solution turning into a solid. But since the water, more and more of the water is evaporating, more and more of the aqueous will start turning into a solid. So it's not really a true closed system here. So that you're still having a transfer of material, but you're transferring more of the aqueous into a solid phase. Hopefully that makes sense. Now, the part that we'll be dealing with mostly here is what's referred to as chemical equilibrium. So at equilibrium, macroscopic or observable changes no longer occur. In other words, if it's something that has a color to it, you will not see any more change in the color. Sometimes it could be the temperature, sometimes the pressure will be changing anymore. So basically it's kind of like looking at a 2-liter pop bottle again, is that when it's closed, when it's at a point of equilibrium, you're not going to feel any change in its pressure. So if you ever squeezed a 2-liter pop bottle, you'll notice it has a certain amount of compressibility to it. And now when you throw it out of equilibrium, you'll feel many times here where it'll begin to tighten up a bit. But when it reaches a point of equilibrium, it will have a certain amount of give to that plastic bottle. So in this case here, reactions can go in two directions, either forward or reverse. The forward and reverse reaction rates are equal, and the concentrations of reactants and products remains unchanged. So under suitable conditions, all reactions are reversible. Now that's one thing that sounds kind of odd here, is that basically all reactions can be made into a reversible reaction. In other words, you can undo the reaction that has taken place. And now some reactions are a little bit more difficult than others to do. Okay, so under suitable conditions, all reactions are reversible. So that means here that a lot of times we look at reactions where they only occur in one direction, where reactants turns into products. We don't look at the other way where products turn into reactants. So, but even though that all reactions are reversible, sometimes the reversible reaction, to reverse that reaction, is going to be a lot more difficult to go in one way than the other way. So for example, if you were burning a piece of wood, to unburn wood will be extremely difficult to do here. Now, it's not to say that if you can't unburn a piece of wood and end up having it back to a piece of maple. But you can get the stuff here, in other words, like the starches and all the different types of hydrocarbons. You can bring those back here, but it's not to say that you can take a piece of maple, burn it, then basically unburn it and get a piece of maple. But you can get the raw ingredients back of what the maple was originally made up of. So I had heard here recently that within the past few years, some people here had, I guess, I don't know if it was for fun or what here, was able to uncook a hard-boiled egg. In other words, if you when you cook an egg here, the white turns into kind of a white solid. The yolk also turns hard as well. But they found a process of basically uncooking the egg, and to me, I think that's kind of amazing here. So basically, again, all reactions are reversible. Just a lot of the reactions that we're mostly familiar with here, it's very, very difficult to make them become reversed. But the ones we're going to be looking at most often here are the ones that are a little bit more easier to reverse. So in a chemical equilibrium, one thing to notice here, this is a compound of N2O4. And when N2O4 is cold, and I'm not sure if you can tell this or not here, but this is like a container of ice. When N2O4 is cold, you have your 2 nitrogens, you have your 4 oxygens here on the ends of this. But as it begins to warm up, the N2O4 will begin to decompose into NO2. So initially you have nothing but N2O4. Then as it begins to heat up, some of the N2O4 will decompose into NO2. NO2 is this nitrogen and 2 oxygens. So basically the 2 nitrogens here in the middle, the bonds in between here will break, and then producing an NO2 here and a second NO2 over here. And then as the temperature continues to increase, as you can see here, the ice is now turned into liquid water here, is that you end up having more of the NO2s and less of the N2O4. But if you maintain this temperature right here, the amount of NO2 versus the amount of N2O4 will remain constant. So in other words, during this, when it's being held constant, right now we have an NO2 here and have another NO2 here. These two can bond back together to make N2O4. But as soon as that happens, something like this one right here would then split apart to make NO2. So in other words, it would always maintain a fixed number of NO2s and N2O4s at a very specific temperature. And that's something that is used quite a bit in chemistry here. So again, you have nothing but N2O4. It begins to shift over to NO2. And once the temperature becomes equalized here, this reaction also becomes equalized here. So as soon as the 2 NO2s join up, they'll make N2O4. And as soon as an N2O4 is produced here, some of those will split apart into NO2. So if you plot out what's happening, so for example, if you look at the concentration, you have at the very beginning, you have all N2O4, but you have no NO2. So if I go back to this, right here at the very beginning, you have nothing but N2O4, there are no NO2s. Then as the reaction continues on, the amount of N2O4 is going to start dropping, but at the same time, the amount of NO2 will also start increasing. Oops. And that's what you're seeing here, is as time goes on, in this case here, you only have 4 of these NO2s, and you have a lot more of these N2O4s. And so that's what you're seeing here. And then eventually, it'll reach a point where, as the temperature goes up, you're getting more of these NO2s, and you're having less and less of this N2O4s. But there's a point where no more of the N2O4s will break apart, and there won't be any more net change of the NO2. So that's what you're seeing at this point right here, is that this now remains fixed. Now, it's not to say that the molecules don't break apart and reform. As a matter of fact, they are actually constantly doing that all the time, but the total net amount is always remain a fixed amount. Now, if you look at the rate which is taking place here, is that the rate of change that's happening with N2O4 and the rate of change of NO2 is going to remain, is going to be changing here all the time here. So initially, the rate for the N2O4 is going to be really high. If you could tell, remember with the slope of the line here, you draw tangent to the slope of the curve. So over here you have a very rapid change which is taking place, and then as it gets closer and closer, it's going to start slowing down, And finally, these two will become the same. And this is kind of similar to, if you remember, for those of you who've taken physics, this is kind of similar to, if you remember, with your distance and time. So let's say you have your distance over here, you're measuring your time, and you're looking at an object which is accelerating. So you end up getting this curved line that's going up. And that's kind of what's happening with this, is that we have this, the total amount which is taking place over a period of time is always changing here. In other words, you're looking at a concentration versus time. It's kind of like looking at your distance versus your time. But then, if I were to take something like this and plot it out, I'm now comparing the velocity versus time. It's kind of the same thing that's happening with this. You have concentration over time, so concentration over time is your reaction rate. The same way that distance over time is my velocity. And what ends up happening here is that you end up getting a line. If it's a constant acceleration, you end up having something with a constant slope. It's kind of the same thing that's happening with this, is that once these two reach, then there is no more change which is taking place. So there's no more net change of how quickly the reaction is taking place here. Basically, for all intents and purposes, the reaction has stopped. But again, there's a constant net change, or the amount of net material will always remain fixed. So the equilibrium constant. So why would we want to know the concentration of the reactants and products at equilibrium? Well, I'm glad you asked that. Simply put, if the concentrations of reactants and products are known, then the reaction conditions can be changed to maximize the product formation. And this is used quite a bit in industry. This is perhaps one of the big cornerstones of any type of industry that's dealing with chemicals. If you want a certain amount of substance to be produced here, by controlling the rate of reaction, you can control how much of the material is going to be made here, and also even for safety reasons. Sometimes you don't want a reaction to be taking place too quickly. For example, like the process of making fertilizer is actually very, very dangerous. And it takes a lot of monitoring of this rate of reaction. And if you don't monitor it very specifically here, you can end up having a massive explosion. So how can you find this information? Well, I'm glad you asked. So before we get to that here, so the equilibrium constant is designated by the letter K. It's a capital K this time. So with a little k, that represented the rate constant of an equation. The big K, the capital K here, represents the equilibrium constant of an equation. So they're related, but they're not the same thing. And there are several different types of symbols here. Sometimes you'll see capital K sub C, that stands for the concentration constant. K sub P, the pressure constant. K sub B is the constant of a base. K sub A is the concentration of an acid. KSP is your solubility product. KEQ, that's your equilibrium constant. They're basically all the same thing. You're just kind of designating what type of constant are you looking at. Are you looking at an acid? Are you looking at base? Are you looking at something that's at equilibrium? So basically they're all kind of the same thing. It's kind of like sometimes in physics here, if I write down like V sub car, if I can spell here, or V sub person, you get the idea here. This is not easy to do on a computer here. Okay, so it's kind of the same thing here. We're looking at velocity, but we're also kind of designating exactly what are we looking at. And that's basically what's happening with these here, is that don't be too concerned here where all of a sudden, oh, this is an EQ, and this is an S, and this is an A, and this is a B. It really doesn't matter that much. Okay, just let the reader or the user know what exactly are they looking at. So to find the K, the constant value, it is simply the concentration of the product in the numerator, each raised to the power equal to the coefficient of that substance in the chemical equation. The concentration of the reactants are in the denominator, each raised to a power equal to the coefficient of the substance in the chemical equation. Does that make sense? So I think it will be a little bit easier to understand here if you look at the formula. So let's pretend we have this reaction. You have A plus B producing C plus D. The A, the lowercase letters here, represents the coefficient numbers. The capital letters represent the substance. And so the constant is basically the concentration. Remember, the square bracket stands for concentration. It's the concentration of the product over the concentration of the reactants. And so if the lowercase letters represent the coefficient numbers, you're putting the product, so C and D, over the reactants A and B. And so if you look at these right here, the K is your constant. The coefficient numbers are your lowercase letters. The compound is your capital letter. The square bracket is a concentration, a lot of times in molarity. Sometimes it can even be in pressure units. For example, like pascals or atmospheres or something like that. So again, if you notice here, so we're putting the products C and D on top, and it's raised to a power that's equal to its coefficient number. So C raised to the power of C, D raised to the power of D, all over your reactants, which is like A raised to the power of A times B times raised to the power of B. And what happens here is that this produces a constant value. And you can look in chemistry textbooks here or chemistry reference books here, and for a specific type of reaction, you can look up what is the constant value. It's kind of similar to like in physics. For example, you may have like a piece of wood on sliding across a piece of glass. There is a coefficient value. There is kind of like a constant value which is taking place out of that. If you're looking at thermal expansion, there is a constant value for the expansion of aluminum, which is going to be completely different than the constant value that's used for the expansion of brass, or the expansion value for steel. So each reaction has its own unique constant value. Now, one important thing here to also note here is that pure solids and liquids are left out since the concentrations will not change. So, for example, if you have water, a lot of times you're going to leave that out. Now, there's actually sometimes here, though, that you will actually leave water in here. In other words, it sounds kind of weird that you're making water and it's already dissolved in water, but it's actually you're looking at what is the concentration of the water in the water solution that's already in there. So it only includes substances that can change concentrations, such as gases and solutions. So a lot of times it's going to be either a gas or something that's going to be aqueous. So to determine the equilibrium constant, reaction must be balanced. So give you an example here. 2 sulfur dioxides plus oxygen will produce 2 sulfur trioxide. And so it has to be balanced, like 2 sulfurs, 2 sulfurs. Here you have 2 times 2, you get 4 oxygens, plus 2 more, so you have 6. 2 times 3, you get 6 oxygens over here. So after equilibrium is reached, the concentration of the reactants and products should remain constant. So a ratio of their concentration should also be constant. So to find out what is the Kc, the constant concentration of this, it's going to look like this. All right. So again, you put your products on top. You're going to put your reactants on the bottom. Okay. So if you know the concentration of your sulfur trioxide, SO3, and the reason why this is raised to a power of 2, that is the same thing as your coefficient number. Okay. And then you have your reactants on the bottom. So you have your sulfur dioxide, SO2. So you have SO2, and you have the concentration of that, so it's in the square brackets. This has a coefficient 2. This is raised to the power of 2. The oxygen, so you have the concentration of the oxygen, O2. And because there's only one oxygen here, technically there's a 1 over here. So a lot of times you don't, when it's raised to a power of 1, that's the same thing as basically not doing anything at all. So that's the reason why you don't see a 1 over here. But you could put a 1 in there anyway. So in other words, what this means is that there is a constant value that is being produced here with the sulfur trioxide raised to the power of 2 all over the concentration of sulfur dioxide raised to the power of 2 and the concentration of oxygen. So I can find the concentration constant. What does it really mean? Again, the Kc helps determine the product yield. So what would be favorable for our product yield? So basically there's 3 different situations that occur with Kc. So we're going to take a look at those. So if the constant is less than 1, basically a forward reaction occurs only very slightly. So therefore the reactants are being favored. So in other words, the reaction is, if I were to write this out, so you have A and B. So what this means here is a forward reaction occurs only very slightly. The reactants are favored, which means this reaction prefers to go to the left. Okay, so this is my reactant, this is my product. The reactants are favored. Now, let me go down to this one here. If K is greater than 1, especially if K is like really large here, then what that means is this. So if I have my reactant is A and my product is B, then the products are favored. In other words, the reaction prefers to go in this way. And this is what we most often look at, is a lot of these will have a K value that's greater than 1, so it's more likely to go towards the right. Now, if it's basically 1 or something pretty close to 1, then what we have here is this is my reactant and this is my product. Then we're going to have a reversible reaction. It's going to be taking place in between here. So if this is exactly 1, in other words, A can very easily turn to B just as easily as B is able to turn into A. So if it's less than 1, the reactants are more favored. If it's greater than 1, the products are more favored. If it is 1 or basically close to 1, then both of these are of equal ability to in order to change into its other original material. So it's kind of like using the analogy where my son and I were dumping water, and so this would be kind of like, you know, if my son had the big cup and I had a little tiny cup, you know, we're dumping the water into each other's container here, is that the reaction is more likely to go towards my direction here. Even though I started off with A, I learned all the A, and there was no B. So I'll take a little bit over to the side. He was able to take a lot more. So the reaction is going to be favoring this side. And this situation here will be where if I had the big cup and he had the little tiny cup. So the reaction is more likely to go towards this direction here. And in this situation here is if our 2 cups were the same size. So even though I had all the material over here, I start dumping over here, but he's able to just as easily dump it back to my into my container here. And so eventually those 2 containers will reach a point of equilibrium. So let's take a look at an example. So write a chemical equilibrium expression for the reaction. So if you have hydrochloric plus oxygen making chlorine and water. Okay, now remember again what was said about water here. It sounds kind of weird here, but this is also a gas as well. But you put your products over your reactants. And if you notice the coefficient numbers, or the coefficient numbers are raised to that power value here. So if you know the concentration really in any one of these or even all of them, you can find out what is your Kc value. What is your constant value for this particular type of reaction. So you have 2 chlorines, you have chlorine, concentration of chlorine raised to the power 2. You have 2 waters, so you have the concentration of water raised to the power 2. And then for your reactants, you put that down as your denominator. You have 4 hydrochlorics, so you have HCl raised to the power 4. And you have 1 O2, so you have a concentration of oxygen raised to the power of 1. So at equilibrium, let's say that concentration of hydrochloric is 0.0625 moles per liter, or that's also what's referred to as molar. And the hydrogen and chlorine both have a concentration of 0.045. So by looking at this, if you want to find out what's the concentration of Kc, so we know the concentration of HCl is 0.0625, and H2 and Cl2 both have a concentration of 0.045. So this is 0.045 molar, and this is also, 0.045 molar. So to find out the value of the constant concentration, it's going to look like this. So again, you're going to put your product on top. So you have hydrochloric, you have a coefficient of 2, so raised to the power of 2. Both of these have a coefficient of 1. So you have the concentration of hydrogen times the concentration of chlorine. Both of these are raised to a power of 1. And if you substitute the values to it, so hydrochloric had a concentration of 0.0625 molar. So you can put 0.0625 in here. And then your hydrogen and your chlorine, both of those had a concentration of 0.045. So you're going to take 0.0625 squared, all being divided by 0.045 times 0.045. Now, if you're doing this in the calculator, one thing I would strongly urge you to do is, it's a common mistake a lot of people make here, is you're going to take 0.0625, squared it, and then divide it by, and then open up a set of parentheses. You're going to take 0.045 times 0.045, close parentheses. Okay. When you do that, you end up with the concentration of 1.9. Now, if you remember, going back, this, because it's 1.9, this reaction favors the product. In other words, the reaction is more likely to go to the right. So in other words, even though this reaction is reversible, you're going to have a lot more of the product than you are of the reactant. So a little review here. You first want to write a balanced chemical equation. So make sure the reaction is at equilibrium before you write the chemical equation, because if it doesn't balance, it throws everything else off. Second step, write an equilibrium expression. To write the expression, place the product concentration in the numerator and the reactant concentrations in a denominator. In other words, your products go on top, your reactants goes on the bottom. The concentration of any solid or pure liquid that takes part in the reaction is left out because these concentrations never change. So basically, if it produces a solid, most often if it produces a solid, just leave it out. If you don't see it being specified, then go ahead and leave it in. So for a reaction occurring in an aqueous solution, water is emitted because the concentration of water is almost constant during the reaction. Now, I've seen sometimes where they'll leave it in there, especially if it's a gas. But if it's liquid water, most often you leave that out. And then complete the equilibrium expression. To complete the expression, raise each reactant's concentration to a power equal to the substance coefficient and the balanced chemical equation. And so going back, basically it's this right here. These are your coefficient numbers. You have 2, a 1, and a 1. And the reason why is because you have a 2, a 1, and a 1. Now, I'm going to show you something which is called an ice table or a rice table. Now, me personally, I have been used to calling it an ice table. Some people might refer to it as a rice table. And if you remember the chart method, kind of Souder stoichiometry, it actually looks kind of similar to that, except I didn't create this. This has been around for a very long period of time. As a matter of fact, I didn't learn about this until long after I had came up with my chart method, but it has some similarities to that chart method. So it's a way of organizing data about equilibrium systems in order to make problem solving a little bit easier. So the rice or ice stands for this. So the R stands for the reaction, I stands for the initial concentration, C stands for the change in concentration, and E stands for the equilibrium concentration. Now, sometimes I've been used to calling it an ice table, and the reason for that is because you're just looking at these right here. Okay, the reaction is kind of assumed. So you write down the reaction, and then you write down ICE after that. So let me show you how you go about doing that. All right, so let's pretend we have this reaction. A plus B produces C and D. We have some sort of equilibrium reaction which is taking place here. So along the left-hand side, you're going to write down RICE. Okay, the R is where you're going to write down your reaction. And personally, I kind of prefer putting in over here, just drawing on here, a double-sided arrow. Pretend that's a double-sided arrow. Okay. Now, for the I part of it, this is where you're going to record the initial concentration of substances. So typically the products will be 0 because initially there will be no, will not be any products. In other words, right at the very beginning, you have nothing but reactants, but you have no products. So you're going to write down what is the concentration of A and what is the concentration of B. But for C and D, there's nothing because before the reaction starts, none of this exists. So both of these are going to be 0. Now for the C, which stands for the change, you're going to write the change that each substance will go through based upon the coefficients of the reaction reaction. So the reactants are negative because they're losing material, products are positive because they're gaining material. And so basically this is based on the coefficient number. So the fact I have A up here, so if A is a 1, then this would be minus 1x. Let's pretend if B was a 2, this would be a minus 2x. And the same thing over here. Because your products are gaining material, both of these are going to be positive. So if this was a 1, then it would be a positive 1x. If this was a 3, then this would be a positive 3x. So again, your reactants are negative because you're losing material. Your products are positive because they're gaining material. And you're just putting x after all of these, but it's the number that appears in front of the x is your coefficient number. Then use the initial concentration I and the concentration change C to write an expression for the concentration of each substance when it reaches equilibrium. So this is before the reaction, and this is the point when it reaches the point of equilibrium. That's what E stands for, is equilibrium. So when it reaches equilibrium, all you're doing is combining these two together here. So A minus AX. So that's what you have down here. So concentration of A is minus AX. You have concentration of B minus BX. So you have B minus BX. Then you have 0 plus CX. So 0 plus CX. So basically since 0, you don't need that. You can just write down CX. And 0 plus DX. So you have 0 plus DX, or quite simply DX. So after setting up the Rice table, insert the values for the equilibrium concentration of any substance for which the equilibrium concentration has been given for the Rice table. So let's pretend that the concentration of D was 0.5 molar. So to determine the value of X, you're going to take 0.5 molar is equal to dx. So kind of going back to this here, if D was equal to 5 molar, so 5 molar is going to equal to dx. So what we have to do is we have to solve for what is X. So we take 0.5 molar is equal to dx, and then in order to solve for X, we have to divide whatever D is here. So for example, if there's a coefficient of 1, so you're going to take 0.5 divided by 1. If this was D had a coefficient of 2, it would be 0.5 divided by 2. Okay. Now, once you solve for one of the x's, then you're going to use that x to solve for all the other x's. In other words, once you solve for this x value right here, then that's what you're going to plug into each one of these throughout here. So x is equal to 0.5 molar divided by whatever value D is. Whatever value you get here, plug it in here, and that'll give you the concentration of C. Plug it in here, and that'll give you the concentration of B. Plug it in here and get the concentration of whatever it is for A. So after setting up the Rice table, use the calculated value of X to determine the equilibrium concentration of all the other substances. Complete the Rice table by substituting the calculated value of X into the expressions for the equilibrium concentration of all the other species. Now when they say species, that's just like another word for substance, okay, or another word for a chemical. So let's try another one of these here. So how to calculate the equilibrium constant case sub C here using the Rice tables. So write the expression for the equilibrium constant using the balanced chemical equation. So again, A produces B plus C. So you have a decomposition reaction taking place. So the expression for the equilibrium constant here would be the constant is equal to your products. So B raised to the power of B, C raised to the power of C, A raised to the power of A. And EQ here is basically just like any type of substance here. So don't worry too much about, because it's sub EQ. So this stands for equilibrium. So substitute the values for the equilibrium concentrations for each substance into the equation and solve. The concentration of each substance at equilibrium is given in the bottom row of the Rice table. So let's take a look at this here. So something which is kind of similar to that. And make sure 5 moles of hydrogen and 10 moles of iodine are placed into a 5-liter container at 450 degrees Celsius and allowed to come to equilibrium. At equilibrium, the concentration of hydrogen iodide is 1.87 molar. Calculate the concentration or calculate the value of the equilibrium constant, K, for this reaction under these conditions. So we have the reaction hydrogen plus iodine makes hydrogen iodide. And it's balanced out 2 hydrogens, 2 hydrogens, 2 iodines, 2 iodines. So you can write out the reaction hydrogen and iodine makes hydrogen iodide. And let me put up here. This is where you have your double-sided arrow over here. Okay. So we have 5 moles of hydrogen. So we have 5 moles of hydrogen, and that's in 5 liters. So even though you have these 2 gases both in 5 liters here, it's still in 5 liters here. So you don't divide this in half and say the amount inside of here. So 5 divided by 5 gives you 1 molar. And then you have 10 moles also in 5 liters. So you have 10 moles in 5 liters, so you have 2 molars. Now, before the reaction takes place, there was no hydrogen iodide being produced here, so this is 0 molar. Now, the other key thing is at equilibrium, it had a concentration of 1.87 molar. So at equilibrium, the concentration of hydrogen iodide was 1.87 molar. We'll get to that here in a little bit. Then you're going to let X be the common factor in the concentration change. So this has a coefficient of 1. I'll put a 1 over here. So therefore, and because this is a reactant, you're losing material, so it's negative 1x, or just quite simply negative x. You have a coefficient of 1 over here. So negative 1x, or just quite simply negative x. Again, negative because you're losing material here. And then you have 2x. And this is positive because it's gaining material. So because you have a coefficient of 2 here, that's the reason why you have a coefficient of 2 here. And so at equilibrium, it's going to be equal to whatever original material concentration you had, 1 molar, but you're going to be losing material. This one started off as being 2 molar, you're going to lose a certain amount of material. And this one you started with nothing, but then you're gaining material. And it's dependent upon its coefficient number over here. So you're just taking 1 molar minus x, 2 molar minus x, and that's the reason why you get these right here. 0 molar plus 2x, so you get 0 plus 2x. Then we said the concentration was 1.87 molar of hydrogen iodide when it was at equilibrium. So we're going to plug that into here. So 1.87 molar is equal to 2x. So we're going to take 1.87 molar is equal to 0 plus 2x. Technically, this is 0 molar plus 2x. So because we have this little bit of information here, we can go ahead and solve for what is x. So in order to solve for x, we need to divide out the 2 from both sides. So 1.87 molar divided by 2. So x is equal to 0.935 molar. So in other words, the amount of change that's going to be taking place here is going to be equal to this value here. Now, since we now know what is the value of x, we go ahead and plug those into these 2 problems over here. So now, if I take this value and plug it into here for x, so I have 2 molars minus 0.935 molar, I'll have 1.065 molar of iodine, And the same thing with this. If I plug it into the X over here, 1 molar minus 0.935, I'll end up with 0.065 molar. So in other words, when this reaction reaches a point of equilibrium, if I have at equilibrium, if I were to have 1.87 molar, then also at equilibrium, I will have a constant concentration of iodine of this amount right here, 1.065 molar, and also I have 0.065 molar of hydrogen. So this is kind of like, again, doing the parts where we're dumping cups of water into each other's container, is that when it reaches a point of equilibrium, we just find out how much was in each container at the point of equilibrium. Now, to find the value of Kc, since now we have the concentration of the hydrogen iodine and hydrogen iodide, we can now plug that in to find out what is the constant value. So that means if I take the concentration of hydrogen iodide, so I take my product over my reactants, so hydrogen iodide raised to the power 2 because I have hydrogen iodide and I have a coefficient of 2. All over my reactants, the hydrogen raised to the power 1 and iodine raised to the power 1 because hydrogen and iodide both have coefficients of 1. And then we're just plugging the values here. So 1.87 molar, that was a concentration right here. So I'm going to plug that into here for my concentration, my molarity. And the same thing for my iodine, 1.065 molar. So I have 1.065 molar, and my hydrogen was 0.065 molar, so I have a concentration of 0.065 molar over here. So I'm going to take 1.87 squared, and again, what I would recommend doing is to close this up in parentheses. So divided by 0.065 times 1.065, close parentheses. And when you work this out, you end up getting a value of 50.5. So this is a constant for this particular type of reaction at that temperature. So at 450 degrees Celsius, this will have a constant value at 50.5. And again, because this is greater than 1, that means this reaction very strongly favors the hydrogen iodide. So in other words, sometimes you might see it drawn out where you have a big arrow pointing to the right and a little tiny arrow pointing to the left. In other words, some of it's going to be turning into this, but most of it's going to be turning into hydrogen iodide. Now, let's take a look at another one. For the reaction below, what is the concentration of each substance at equilibrium with a constant concentration of 0.98, and the initial concentration of C2H4 is being 0.33 molar and hydrogen 0.053 molar. So this time, we know the concentration of the C2H4 and the concentration of hydrogen, and we don't know the concentration of C2H6, but you do know the constant. And again, this can be looked up in a lot of chemistry reference books, is that for this type of reaction to produce this product over here at a specific temperature here will have a certain constant value to it. So this actually allows you to be able to predict here where if this reaction takes place, what direction is it most likely to go. And then also if you know how much of these two reactants you have, you can even figure out how much of these products are going to be produced here. So again, we're going to have to set up the Rice table. So you have write out RICE. Now normally whenever you're doing this, you don't put this part in here, but this is just kind of a little bit of a reminder. So you have your reaction, you have to balance it out. So 2 carbons, 4 and 2 is 6 hydrogens, and 6 hydrogens over here. And I'm going to put down the yield symbol over here, just so we know. So these two are losing materials, and these both have a coefficient of 1, so it's minus x and minus x. And this also has a coefficient of 1, so this is going to be a positive x. And then you're going to take 0.33 molar minus x, so you end up with this. And this is going to be 0.54 molar minus x. Oh, I just noticed here I have a typo here. Okay, they're both about the same here. I don't know what was going on here, so this should be 0.53 molar, not 0.54. See, no one told me about that. You guys weren't paying attention here. You should have told me. And then over here, initially, before the reaction took place, he didn't have any of the C2H6, but it's going to be changing by this amount. So therefore, 0 plus X is just going to be X. Then you're going to set up your equilibrium expression. And so the constant is equal to C2H6. So your product over your reactants, C2H4, H2, all these have a coefficient of 1, so they're all raised to the power of 1. But again, this has a constant value of 0.98. So this right here equals 0.98. Now, we want to know what is the concentration when it's at equilibrium. How much, if I know I have this much of C2H4 and this much hydrogen, I want to know at the end when it reaches equilibrium, how much C2H4, how much H2, and also how much C2H6 will you get? So now we're going to have to do a little bit of mathematical gymnastics here. So let's go ahead, and since we have these values here, we're going to have to plug these values into the equation over here. All right, so when you plug those numbers in, you end up getting this. So 0.98 is your constant. C2H6 is X, so I have X over here. C2H4 is 0.33 molar minus X, so 0.33 molar minus X. And H2 is 0.53 molar minus X, so you have 0.53 molar minus X over here. And we want to solve for X. So therefore, next step here is, since I have these two as a denominator, I need to bring this up. So I'm going to basically multiply both of these by my denominator here. Oops. So now I'm going to have to solve for X. Okay, here we go. I don't know what happened here. And so, actually, before I start cross multiplying here, so what I'm going to do here is 0.33 molar. You guys remember doing this in your math classes here. So 0.33 molar times 0.53, you end up getting this here minus X 0.53. So this is where you have to distribute these values here. So you end up with X squared minus 0.86X plus 0.1749. And then, since I have this entire value down here, now I want to go ahead and bring this out of the denominator. So I want to multiply this whole value by this value right here. So I end up getting, when I multiply this out, I end up with 0.98 times this entire expression is equal to X. So now, because I have 0.98 sitting out here, I need to distribute that value into everything inside the parentheses. So I end up with this, 0.98x squared, 0.8428x plus 0.171402 is equal to x. Now, I have an x here. I also have an x over here. So I want to combine my two x's together. So I want to bring this x over to the other side. Now, if you remember, now I have to subtract x out of here. So when I do that, and technically, this x here is a 1x. So when I bring it over here is when I switch sides, I have to switch signs. So I have negative 1x and 0.8428x. And I end up with, oops, come on now, with this here. So when I combine these two values together here, I end up with negative 1.8428x. And then, I have x here, I have x squared, I have x, and I have nothing over here. How do you solve for x? How would you solve for x? So I want to know, any ideas? Oh no. Guess what needs to be used? Dun dun dun. Yes. Hopefully you recognize this. It should be cheering. It's like, yes, yes, quadratic equation. So, therefore, here is your A, here is your B, and here is your C. You guys remember the song here? Good, because I don't remember that song here. So, hopefully I can hear you guys sing it already. So, we need to solve for x, and the only way we can solve for x here is by using this quadratic equation. So, here it is again. And when you plug it into the quadratic equation, it's going to look like this. And, you know, hopefully you guys are familiar with how to go about doing that here. And as you're well aware, you end up with two answers when you're doing this. One of these is correct, the other one is not. So now we have to find out which one of these two is the correct answer. You thought you could get away from quadratic equations. Oh no, oh no. It's here and it's live and well. So now, because these two x values, one of these is correct and the other one is not, what you have to do is you have to test them. So we don't know which one of these is the correct one. So we're just going to pick one of these right here. So for example, if I use C2H4 and I have a 0.33 molar minus X. So all I'm going to have to do is just plug each one of these and solve for X. So when you do that, so I have 0.33 molar. If I try using this one here, end up with this value, end up with this answer over here. Same thing with this one. I have 0.33 molar minus X, and if I try using X for this value right here, and when I subtract them, I end up with this value here. Now, if you notice, with this one here, I have a negative value here, which is to have a negative concentration really cannot happen here. So that's an indication here that this right here does not work. Pretend that's an X here. So therefore, this is the one you do not use. This is the one you're going to have to use. So this one right here is the one we want to use. So this is the correct one we want to use. So now, since we identified what X is, we can now go ahead and start plugging that into this equation here. So for C2H4, if I take 0.33 molar minus X, I end up with 0.23187 molar for my C2H4. For hydrogen, I'm going to take your 0.53 minus the value for X. This would be the concentration of the hydrogen. And for C2H6, when you end up doing that here, end up getting, since it's just X, it's going to be exactly the same number here. Okay. So these are going to be your concentrations of each one of your substances. So when it reaches a point of equilibrium, we just identified how much of the C2H4, how much of the hydrogen, and how much of the C2H6 you would get. Okay, so hopefully that made some sense here. What I'm going to do is I'm going to be posting an assignment onto your Google Classroom, and I'm going to give you guys here a few days to work on that. And if you have any questions on it, let me know. And so hopefully all of you are doing well. And the next thing we'll start getting into also is related to equilibrium, but it's what happens when you cause a stress onto the equilibrium and what happens to the reaction. It's kind of a unique type of situation here. So you guys take care, and I will talk to you later. Bye-bye.